Hello, I am Macilia, a PhD student, presenting a study called lattice plasmon coupling in cobalt nanoparticles arrays combining optical and magnetic properties. Known as an efficient and commonly used magnetic metal, we are proposing here an optical study to evaluate plasmonic properties of cobalt. So we choose a structure that consists in periodic arrays of cobalt nanodisk deposited on an ITO-covered glass substrate. The structure is fabricated by electron beam lithography and probed with optical spectroscopy. The experiments are supported by FDTD calculation using a home-developed code. Let's first evaluate the capability of cobalt to sustain localized surface plasmon resonance LSPR by considering an array with typical dimension sustaining LSP mode. Both calculated and measured spectra agree to display a strong extension indicating the excitation of LSPR confirmed by the mapping of electric field intensity showing a mode of dipolar nature. We also observe a sharp peak at 470 nanometers attributed to a waveguide mode in the ITU layer. Since the electron beam lithography allows the tanning of morphological parameters, we investigated the impact on resonance when modifying the diameters. As expected, the resonance seems to redshift when increasing the diameter of the nanoparticles. The observed resonance is found to be broad due to the very lossy metallic nature of cobalt. So we are proposing to take advantage of the grating effect by inducing surface lattice resonance that can significantly improve the quality factor. Thus, we report that the resonance narrows and redshift when increasing the grating constant, so we have an improvement of the quality factor. Also, the quality factor is found to be the highest when the diameters are the smallest. A relevant question now is the chemical stability of the metal in air. We show that the resonance redshifts a little after 35 days, then remains constant. This shift results from the increase of the refractive index of surrounding media due to the thin layer of cobalt oxide covering nanoparticles, which allows later on to the resonance to remain constant. In summary, we evaluated the optical response of cobalt nanostructures. We showed that they can display well-defined LSPR in the visible range. The morphological parameters have a significant impact on this resonance. We also achieved an improvement of the quality factor by taking advantage of the grating effect. We addressed the question of chemical stability, which seems to not be critical since we have a passivating thin layer on the cobalt nanoparticles that keeps the optical response constant.